and minus, and this is over time. So we feed this signal into the vertical plates. Basically, if I've got an AC generator, that's where it goes. It makes the beam that is emitted from an electron gun and hits a phosphor screen and produces a dot there. It makes it move up and down in correspondence with that waveform. But all you'll see is a vertical line. So how do you make it look like this? Well, what's going on here? This is time. Time operates at a current rate. So what I need is something that produces a ramp-up voltage between these two plates. Something will ramp up like that, so it'll start up, the beam will start out on the left side when we're in the negative territory here of this axis, and work to the positive side. But then it's got to do it over and over again. So basically this thing is going to drop down and repeat itself. This is a sawtooth. It looks like the teeth of a ripsaw wave. And basically it's going from left to right and then rapidly retracing, going left to right again. Now this guy's going up and down. This guy's going in a very linear fashion from left to right. You put the two together, and there's the waveform with time moving at a steady rate, and then going back and repeating it, and going back and repeating it as this thing decides to make its oscillations happen. And that's how we look at a waveform like this that's not direct current. And then we put a little grid on this scope. I'm putting a lot of lines here, I know that, but you know, if they put this thing called a reticle in front of it, you can actually count the centimeter squares and say, okay, according to the amplifier in that oscilloscope, each centimeter represents so many millivolts or microvolts or actual volts. And you can measure that voltage. You can measure the peak, and you can measure the shape, or you can look at the shape. But how do you deal with the fact that the peak may not be what you're getting out of there? After all, think about this. Here's my waveform. It's only at this peak value for an instant. It's only at this peak, negative peak value for an instant. So what is the direct current equivalence of this? It's going to be something less than the peak value, we know that. The mathematicians looked at this thing, analyzed it, and says, okay, here's what we compute to be the equivalent DC value of an alternating current. We have taken the square root of the average squares of the voltage that have been added up from the first one to the nth one. And you look at that and say, help me out here, what does that really tell me? It says that there is actually a formula for figuring out what this DC equivalent is. And what it really turns out to be is if this thing is a sine wave, and most of the time it will be, especially if it's coming out of a wall socket, it will be 0.707, which happens to be 1 over the square root of 2, by the way, of the peak value. So if you had 100 volts here, the DC equivalent would be 70.7. Pay attention, that's going to be on the test if you go for a general and extra class license. That is the conversion between RMS, or root mean square measurement of voltage. And by the way, if you look at an AC voltmeter, it'll say it's a true RMS voltmeter, meaning if the waveform is not a sine wave, it will compute what the, it has internal circuitry that will figure out what the real addition of all the harmonic content is that will give you the DC equivalent. And if it's not a true RMS meter, you might not get that value if you are not looking at a sine wave, but you'll get something close. Now you'll ask yourself, what's the average value here? Obviously, it spends as much time above as it does below, so the average is going to be 0. Well, what's the average value if this thing is, rectified so that it's always in the positive sense? It's gonna be a little less. I forgot the exact value. I think it's 0.5 something, but whatever it is, it's going to be less than the RMS value. It's not typically what you're gonna find on the test. RMS and peak are really what's going to be there. And by the way, be very careful here. There's a difference between 0 and peak and peak to peak, which is negative and the positive peak values, or what they sometimes refer to when you look at, for instance, single sideband power measurements. They talk about PEP, which is peak envelope power. That means from the extremes. And that will be double the 0 to peak value. So you have to be you have to pay attention to the way the question reads. If the value is 70.7 volts RMS, what is the peak to peak value? Well, it's going to be 200 from here to here. It's going to be 100 from 0 to here. Just a little pointer. All right, that's measurements for the most part. Let's talk about some of the other things I want to bring up. I'm going to save the math for just a little bit longer because I said during this analog to digital discourse that I really owe you a better discussion on the transistor, what it is, how it works. And I think since we have enough time, I got an hour and a half to go, we can cover it and cover all the other things pretty successfully. It might not even take 2 hours to do this whole thing, in which case I'll search for some other loose topics that I may not have covered. Let's really give this guy a good look. Got a pen with some decent color to it. That should do it. This, I think most engineers will appreciate, is one of the most incredibly useful inventions in electronic history. There's a lot of useful things, the vacuum tube's not the least amongst them. But the transistor is why we have desktop computers. It has everything to do with modern electronics, the cell phone, you name it. The fact that we could put so much amplifier and switching and other capabilities of electronic devices into such a small space would not have been possible. You couldn't just paint it on a silicon wafer the way we do with transistors. Vacuum tubes would always have to be a bottle with air extracted from it and metal components that emit electrons, receive electrons, and control the space charge between those 2 devices that are called the cathode and the anode, or sometimes called the plate. But it's really the anode and the cathode. And the thing in between that controls space charge, referred to as the grid. That thing brought us amplifiers, oscillators, all the things in the modern electronic era, but it takes up room. Anybody that grew up in the 50s and 60s like I did, or our parents before that, remembers a desktop radio taking up some real space, and a portable radio requiring a very expensive battery pack that had A, B, and C batteries. The A batteries would feed a thing called a filament, about 6 volts. That would heat up the cathode, and between the cathode and the anode would be a high voltage thing, about 150 volts or more, and then the grid would be fed with some other, typically turned in negative direction, about 100 volts or something like that. You'd have to have a battery pack that had all of those voltages in it to make a vacuum tube work, and then you had a number of vacuum tubes in the radio, so it was a big thing. The irony is everything in our electronic era has gotten smaller except for radios. So we got the boombox. But that's not because of the electronics, it's because of the speakers, and the CD player, and the other devices on it. Okay, so what was the big improvement here? transistor. Every transistor has 3 leads coming out of it. No more, no less. There really aren't too many exceptions. There's a phototransistor which might have a window for light to enter in lieu of that thing over here, which we call the base. And this thing up here is called the collector. And if you got a collector, you should have something else called an emitter. So the collector is something to collect. And that's it. Transistor's got 3 leads, 3 points of attachment. This arrow is always the one where the emitter is in the circuit. The direction the arrow goes defines it as being an NPN or a PNP kind of transistor. They have to be one or the other. NPN. That's negative, positive. What do you think the third word is? Negative. Referring to the material that this guy is, and this stuff in between is. And what do you mean stuff on each end and something in between? Well, let me draw you a picture of a transistor a little differently. There's your collector. Here's your base. And here's your emitter. They're really stacked one on top, one next to the other. The one thing I can assure you is the base has to be in between the emitter and the collector because it provides a controlling function. What kind of controlling function? Whatever current, this is a current source, goes in this loop will control the current that flows in this loop. In other words, current is going to flow from here to here, but it's going to get regulated by what comes in there. Now it doesn't seem like such a difficult thing to understand. This is a valve, just like the vacuum tube is a valve. Normally you're going to get current flowing here. I know the electrons go the other direction, but conventional currents, plus or minus. The current is going to flow from the plate to the cathode, just like the current's going to flow from the collector to the emitter, even though the electrons are emitted by the emitter and they're collected by the collector. And the thing in between, the grid here, is going to have the same kind of effect as the base has here. It's just they do it differently. This one does it by regulating the space charge in a vacuum. It literally puts up a potential that controls how the electrons flow. This one does it by injecting minority carriers, electrons in this case, into the base, which causes an avalanche effect. So that this guy, which wants to get current to flow to this guy, but can't because this guy's in the way, gets an injection of minority carriers that makes it start to happen. And the more injection, more current is injected, the more the flow. So it has a very analogous set of properties to the vacuum tube. It's just that it does it with current, this guy does it with voltage. This guy does it with electrons being injected in. This guy does it with a space charge that controls the electrons flying across. Different principle, same mechanical effect is the result. And, you know, before there was a thing called a transistor, what really kind of led the 3 great inventors, whose names were John Bardeen, who was later professor at the University of Illinois, and I met him there. Nice, really interesting guy. The other 2, I can't remember the first names exactly. Shockley was one and Brattain was the other. Wilhelm Brattain, I think, was the British guy. And Mr. Shockley went off to Cal Berkeley, wrote a book about racism and intelligence of human beings, and got himself in big trouble. You don't want to get into that subject if you want to be an electrical engineering professor. That's for the sociologists to deal with. But these, that's the thing about scientists. They have their own quirks. Before there was a transistor, there was a diode, which we've studied. Remember this guy? And got some N material here and P material here, and current will flow through this thing with no voltage dropping across, or if you try to reverse the current flow, you'll get a voltage instead. If the current wants to go this way, you'll get a voltage drop. Basically, it's a one-way valve. You're either going to get all current, or you're going to get all voltage. If you try to go forward, it'll give you current. If you try to go reverse, no current, just voltage drop across that device. So if you start with this, and instead of using N and P material, you use N and N material, stick the P material in between, and then inject minority carriers in, you get this so-called transistor effect that gives you the properties it has. And by the way, that base is really very thin. It's only about a micron, about a millionth of a meter large. It doesn't take much to make it happen. It can't be very large because those electrons have to traverse from here to here, or the positive, you know, the conventional current has to traverse in the opposite direction. And you can't have too much material for it to go through. You just need a place for the minority carriers to be injected in to make this avalanche effect work. And you know, you study the subject in a whole course like I took in college, and you get into the depletion layer and all the things that are the physical properties of the transistor, but it really boils down to this. You're providing the missing component for current flow to take place by sticking it in the middle, in the base. The result being, you are regulating a very large current flow. And what you get out of this is